Hi all. Okay, we'll start with the new chapter. It's there in fourth module. Okay, so there's a normalization algorithms. Some algorithms are there. That is think what how to find the minimal cover. Okay, so how to decompose given relation R into 3NF or BCNF. Okay, and some algorithms binary decomposition what to do it. So how we can do it. So those algorithms are there. Okay, and plus some decomposition properties. Okay, so we'll start with decomposition properties. So here, so how design approach will be there is nothing but so you will be having the some relation R. Okay, so in that you will be having the attributes. Then here you will be having the minimal set of FDs. Okay, so it's nothing but you may be having some FDs. Okay, so in that all are not necessary. So in that if I have some basic functional dependencies, so that will be fine. Okay, so nothing but so instead of listing all the things, if I have only some basic FDs, so from that I can derive remaining all FDs. Okay, so that is nothing but minimal cover will come. Okay, so those things will identify, then we'll apply some algorithms. Okay, so if you want to derive it to the 3NF, we'll apply one algorithm. If you want to derive it to BCNF, we'll apply one algorithm. Okay, like that we will be having some algorithms. Okay, then we'll see, so whatever we derived, is it a lossless decomposition or lossy? Okay, so that we will check it, and after that, our database will be designed. Okay, so here what we are doing is, so what is the first property of decomposition we are studying? So in this we have as a something as a property of relational decomposition. Okay, so here we have 5 properties. Okay, that is attribute preservation. Okay, then the dependency preservation. Okay, then is it a lossy or lossless join decomposition, that will identify it. Then testing binary decomposition for non-additive join, this again is lossy or lossless for a binary decomposition. And successive non-additive join decomposition. Okay, so these things will study it. So first one is attribute preservation. So it's nothing but suppose we have one R. Okay, so in that some 10 attributes are there. So whenever you are doing a decomposition, so you have to make sure that those attributes should be there in any one of the table. Okay, so it should not happen as a whatever attribute is there in my relation R, that itself we have to miss it in after decomposition. Okay, so whenever you will do the decomposition, you have to make sure that attributes should be there. All attributes should be there in at least one of the table. Those all attributes should be there. Okay, so something, but suppose I have 10 attributes, so if I decompose into 3 tables. Okay, so first table maybe have as a 3 attributes, second table maybe have as 4, then third table maybe have as again 3. So that's 10 all attributes has to come in different tables. Okay, so like that you have to decompose it, so you should not lose any attribute. Okay, then dependency preservation. Okay, so here whatever dependencies will give it, so there is functional dependencies whatever will give it. So in R, so those functional dependencies should be there in our whatever decomposed tables. Okay, so if I have as a functional dependency x to y, okay, so if I that is there in R. Okay, so whenever I will decompose into, suppose consider the T1, T2, T3 tables, so that x to y should be there in any one of the actually a table. Okay, so it may be in T1 table or T2 table or T3 table, or if it is not there directly, so I should achieve that one by using the closure of F. Okay, so something what here, so whatever F plus whatever we are writing, it is a closure of F. So if you have some attributes that's considered as a, suppose I have say a to, sorry, x to y, one functional dependency in R. Okay, and so whenever I decompose that R into T1, T2, T3, so T1 has something as A and X maybe. Okay, so A and X maybe I have the decomposition attributes. So this A and X, if I use, and if I use the closure on that, so I can get the X to Y, like that. Okay, so that closure should give the our whatever dependencies whichever are there in R. Okay, so here So what we will do is, so whenever we'll perform the union of all the FDs. Okay, so here F stands for all the FDs. So if I decompose this one is a R1. Okay, so R1 to RM tables. Okay, so if I'm doing the functional dependencies, all the union, if I'm doing it, okay, and I'm finding the closure, so it should be equal to the whatever R is there for that. We'll be having the functional dependencies, that closure and whatever we identified here after the union, both should be same. Okay, so I will repeat it once again. So whatever R is given, for that R you will be having the functional dependencies. So that set we are saying is a F. Okay, so that F plus, this is what closure of F for a R should be equal to, so whatever table we will divide it, suppose divide into R1 to RM. So in that also some functional dependencies will be there. So that those are the F. Okay, so here if I took the all the functional dependencies which are after dividing into table, if I did the union, and after that union, if I did the closure of that, so that closure should be equal to the previous whatever R F closure was there. Okay, this should be equal. So this is nothing but dependency preservation. Okay, so normally what will happen is, so it's always possible to find it dependency preservation decomposition D with respect to F, such that each relation Ri in D is in 3NF. So normally after decomposition, so whatever we will do it, that is in D, so always it will be there in 3NF. So up to 3NF level we can achieve it easily by dependency preservation. Okay, then next one is lossless join property. Okay, this is so whenever we will divide R into uh, n number of tables, that is nothing but R1, R2, RM tables. Okay, so whenever we are decomposing, so whenever you are using the natural join on these things, it should not create a unwanted result. Okay, that is it should not create the additional spurious tuples. Okay, and it should not give the less number of tuples also. That means it should not, whatever R should have, those all things should be there in this after decomposition natural join whatever will do it. Okay, so it should not lose the data also, it should not give the some extra data also, that is lossless or non-additive join property. Okay, so this is the third one. So to do this one we have some algorithm. Okay, so and algorithm, and after that so here also for this one also some algorithms are there. So okay, so whenever we are decomposing the table into 3NF or 4NF, so automatically this property will be taken care. Okay, so same thing here also, lossless and lossy also, for that also non-additive join property also algorithm is there that by default it will be taken care. So if we decompose and you have already table, so how to check is it a lossless or lossy? For that we have the algorithm. Okay, so that algorithm we study it now. So here that is something about testing for non-additive join property. Okay, so say our intention is it a non-additive or additive? You may say as a lossy or lossless. Okay, so this property is there or not. Okay, for that we want to test it. Okay, so what is the input will be there for this algorithm is, input is D, that is nothing but decompose all the tables of R. Okay, then functional dependencies. So functional dependencies of R will be there. Okay, then so what are the steps how we will achieve this one? Okay, so here we are saying is a some one matrix will create it. Yes. Okay, so what this matrix contain is some number of rows and number of columns. Okay, so what is number of row is nothing but, so one row I for each Ri will be there. So suppose if I decompose this one into R1 to RM, so R total 1 to M number of rows will be there. So how many R's are there? So that is nothing but here how many we decompose tables, those many rows will be there. Okay, then what is a column here is nothing but whatever attributes are there. Okay, in R. Okay, so in starting R, whatever attributes are there, those all attributes will be there in this matrix. Okay, so yes, matrix contains number of rows are equal to number of decomposition tables, and number of columns are equal to number of attributes. Okay, so initially this matrix will set it to the that is Bij. Okay, so something but row number 1 column number 2, if you are seeing as a B12 will write it. Okay, so like that that entire matrix will fill it. So after that what we'll do is for each row I, Okay, represented one decomposition table here. Okay, so in that, whatever this table has attributes, for those things what we will mark it in that row, we will mark it as a aj. Okay, aj is nothing but, j is nothing but column number. Okay, so just we will mark it as aj. Okay, then we'll apply some logic here. Okay, this fourth step we will apply some logic here. So after applying some logic here, we'll see the table contains all a's or not. Okay, if it contain all a's, it means this is lossless joint property. Okay, or if any of the row, if it is not contain all a's, it means this is lossy. Okay, so I'll repeat it. If any of the row in that matrix, if it contain all a's, it means that is lossless. Okay, if any of the row is not contain all a's, means this is a lossy. Okay, so what logic here we have to do is, so here we have to continuously we have to check it. So step by step we have to check it, and there is nothing but previous step and this new step. If nothing is changed, so we have to stop the algorithm. So stopping criteria is, so previous step and current step, whatever we are doing it in that, if nothing is changed, none of the values are in that matrix is changed, means you have to stop it. Okay, so and you have to conclude it. Okay, so that it may be lossy or lossless. Okay, so what all things you have to do is, so each functional dependency, so you will be having the f. Okay, so this is given input, only f you have it. So in input you have the f. Okay, so this f you have to take it. So in that first functional dependency will take it. So all functional dependencies, for that this is the loop. Okay, so outer loop is for the all functional dependencies. So how many functional dependencies are there, those many times this loop will execute it. So inner loop is nothing but, in that whatever will take one functional dependency, in that for x we'll see the column. So whatever that column name, whatever x is there, for that we'll see the column. So if same values are there, means corresponding y value also will modify it. Okay, so if in a column, so if in a column whatever x column name is there, so same values are there. Okay, so suppose two columns has the a, so we'll modify for the column y also its corresponding values. Okay, so whatever, if it is in there, one of the values there as a, means for all the that column will modify as a only. If it is not there, means we'll leave it. So this one will repeat it continuously. Okay, and if x values, both values are same, x column two values are same. Okay, so y none of the column has the a, so we'll set all that entire column as a b only. Okay, so b just one number will give it. Okay, so what we have to do is, how we have to solve this one example will take it. Okay, so here is one example. Suppose he given as a r. Okay, this r, some attributes he given it. So 1 2 3, so three, total 6 attributes he given it. Okay, so 6 attributes. Then he is saying as a, so this one is by using some algorithm or some logic, we decompose it into three things, that is r1, r2, r3. Okay, so r1 contains these two attributes, r2 contains these three attributes, R3 contains these three attributes. Okay, so like this we have decomposed this one. Okay, and this is the F. Okay, so here functional dependency is given, that is ss into e name. Okay, so this open bracket is not, should not be there. Okay, so ss into e name, then p number 2, p name and p location. So this is second FD. Okay, then SSN and P number both together, number of hours. This is the third FD. Okay, so this is the arrow mark, whatever we are saying. In total 3 are there. That is the 3 FDs are there. Here FD1, here this is the second FD up to here. Then this is the third FD. Total 3 FDs are there. Okay, so now how we have to do it? Okay, so what I will do is, just I will open, okay, one side algorithm. Okay, so now we will open the algorithm. Okay, then just now we will see the corresponding values also, so how it will change it. Okay, so here, so if it's off in algorithm, this is a given thing, d is there, so it decomposes into 3 things in our example. So r he given, then f also he given. So whatever input for our algorithm is there, that is given already. Okay, so now first step is, what we have to do is here create a initial matrix S, one S matrix we have to create it. So number of rows should be number of decompositions here. Okay, so we given as a R1, R2, R3, so 3 rows will come. Okay, so 3 rows we have to create it. Then column, that is a J. Okay, so such that attribute AJ attributes are in R. Okay, so already seen here total 6 attributes are there. Okay, so 6 number of columns will come. Okay, so here 1 2 3 4 5 6, these are the 6 columns, R1, R2, R3. Okay, so these are actually our rows. Okay, so this is, so it should be empty starting. Okay, so this is filled. This is after second step actually. Okay, so first step is just to create the dummy one, that is number of rows, number of columns. Just we'll mention it, R1, R2, R3, whatever is given. Okay, there's R1, R2, R3, then whatever attributes he given. Okay, so these attributes SSN, E name, P name, P number, then P location, then hours. Okay, so this is first step. Okay, so second step is, so here each Sij we have to fill it to the Bij. Okay, so here this is Sij, this is nothing but row and column number. Okay, 1 1 means this is B11, so B12, B13, this is first row, third column, first row, fourth column, first row, fifth column, first row, sixth column, like that. Just you are filling entire this matrix. Okay, so all are were initially we are setting to the B only. Okay, so this is just one kind of indication in the sense. So this all B's we will try to convert into A's. So if successfully we converted at least one of the row as a all A's, it means this is a lossless. Okay, so for that we will try it. So initially we given all B's here. Then next step here, what we are doing is, so each row I represent the relation schema Ri. Okay, so each row is Ri, whatever is there. So this is one schema, relation schema indicates Ri. So for that, whatever attributes are there, that is J. So in this, whatever Aj are there. Okay, so for that we have to set it S of Ij equal to Aj. Okay, there's nothing but if R1 contains whatever attributes, R1 contains SSN and E name. Okay, so R1 contains SSN and E name, these two. Okay, so for these two, so instead of B11 and B12, we have to set as a A1 and A2. That is just column number we have to give it. Okay, so here we are giving as a A1 and A2, so remaining we kept as it is. Okay, now we'll go for second row, R2. So R2 contains P number, P name, P location. Okay, so this is P number A3, P name A4. Okay, P location A5. Okay, so this number 3 4 5, these are nothing but column numbers, first, second, third, fourth, fifth, sixth. Okay, so column numbers. Okay, so just we are writing as a A3, A4, A5. Okay, so this is for the first table R1. Two attributes are there, SSN. So A1, for that we are filling it in first row. Okay, so that is for R1 SSN attribute and E name. Then for R2, P number, P name, and P location. So for that we set it. Then for R3, SSN is there for R3, A1. Okay, then after that P number, so P number, that is again A3 here. Then hours, so here A6. So this is after step 3. So after step 3 we got the result, this one. Okay, now what we have to do is, so to take the functional dependencies one by one, functional dependencies we have to take it. Okay, so here x to y, whatever functional dependency is there, this functional dependency we have to take it. Then for each functional dependency we have to check how many rows has the same values of x. Okay, that we have to check it. So now here in this one, okay, so here if you took first functional dependency SSN, that is producing E name. Okay, so SSN to E name. Okay, so these two actually. Okay, so in this x, okay, so here we are saying as a, so in this, for all rows in S that have the same symbol. Okay, that has the same symbols, corresponding attribute for x. Okay, so here my first functional dependency x to y, that is nothing but SSN to E name. Okay, so my S is nothing but SSN. So in SSN column, whichever rows has the same value, that is R1 row have and R3 row have the same value, that is A1 and A1 here also. Okay, so both are same value for this rows. Okay, for these rows and this column now. Okay, that is E name column. So E name column, so if it is different is there, so previously it was like this. Okay, so here these two are the same. Okay, so then if y is nothing but e name, so if these two, for these two, if they are different, so you have to make it as the same one. Okay, that is, if a is there means corresponding one more that in that column, all you have to make it as a only. So this row and this row, so a, that is nothing but here a2 is there, so this b you have to change it to, and you have to make it as a2 here. Okay, so that we made here. Okay, this is with respect to first functional dependency. Then again same thing we have to do it for a second functional dependency, because this is there in loop. Okay, so now second functional dependency is nothing but p number. From that I can derive p name and p location. Okay, so p number, so in this previous table p number. Okay, so p number, this column I have to see it. So in this, how many rows have same value, that is r2 and r3. Okay, these two have the same values. Okay, so for this, so corresponding which one, p name and p location. Okay, so in this for p name, so in this here we have to check it. So these two rows r2 and r3, so if these values are same, so p name and p location, whatever a's are there, if it is contains a, so corresponding column will make it as a only. Okay, so here p name a4 is there, here b34 is there, so this b34 will remove and will make it as this one also a only. So that is what we made it here. Okay, that is a4 we made it. Same thing for a p location. Okay, so here a5 is there, so b35 was there, so what we will do is we will convert this b into a, so that is a5 we will make it. Okay, then actually we would see the, this is corresponding to this functional dependency, or then third functional dependency we have to see it. Okay, so instead of seeing this for third functional dependency, so here if you saw in this row all a's we got. Okay, and our stopping criteria is nothing but if one of the row contains all a's, means this is successfully we got the algorithm result, that is this is lossless. Okay, so no need to check this one, we can stop it here, otherwise you can check it and you can modify it. Okay, that is also you can do it. That is nothing but ssn and p number both we have to consider as a x now. Okay, so here that is ssn and p number, these two together we have to consider as a x. Now we have to see here in this one, first any rows has the same value. Okay, so that time both should have same values, that is ssn and p number, whatever this row has there, same thing is there, should be there in second row also. Okay, so for example here a1 and b13 is there. Okay, so we have to check it for again a1 and b13 only, so this is not there, a1 and a3 is there, so it's not matching. So b21 is there and a3 is there, so same thing is there or not, what to check it, so it's not there. So none of the this column has same values, so this functional dependency we can't use it further. Okay, so we can stop after that also, because all three functional dependencies also over, or by seeing this result here all a's are there in one row, so you can stop the algorithm. So then we can calculate as a this, that is nothing but r3 row contain all a's. Okay, so decomposition whatever we did it, that is r whatever we divided into r1 r2 or r3, these three things, and that is a non-additive joint property it has. Okay, that is it is a lossless joint property is following it. Okay, we'll see one more example. Okay, so same if these. Okay, so f and same relation r. Okay, so both are there, but decomposed into two things, that is d will decompose into r1 and r2. Okay, so instead of dividing into three, previous example it was there as a in three tables we divided, now here we divided into two things only, that is r1 and r2. So what r1 contains is these two attributes, what r2 contains is these attributes. Okay, so this is given. Okay, so now again we will try to apply same thing. Okay, that is same algorithm we'll try to apply. So here first step is again you have to create the s. Okay, so number of rows are nothing but the number of here how many decomposition we did it, that is r1 and r2, so two rows will come r1 and r2. Okay, and number of attributes are nothing but sorry, number of columns are nothing but how many attributes are there. Okay, so 6 attributes are there, 6 these things will come. Okay, so second step says you have to initialize all the cells as a bij. Okay, so corresponding row number column number will give it, so that is b11 b21. Okay, so like that just corresponding all dummy values, that is will initialize all things as a b's. Okay, then third step what we'll do is, so whichever attributes are there in that row Okay, so this table, so whatever attributes are there, that will make it as a A's. Okay, so here R1 contains e name and p location. So e name and p location. So, okay, so for R1, that is B12, we have to remove it and we have to make it as a A2, and p location B15, we have to remove it and we have to make it as a A5. Okay, so that is A2 here and B5 here. Okay, then for the same thing, for each row we have to do it. Okay, so this is for the first row we did it. For the second row, so R2, it has these attributes. Okay, that is SSN, P number, okay, hours, P name, P location. So except E name we have all, so we can mark it as a A1, this is A3, so except this one, so A5, A4, A5, A6. Okay, these things we did. Then fourth step. Okay, so here what we have to do is, so every time you have to check functional dependency. So whatever functional dependency is there, that you have to check it, then corresponding values are same or not, you have to check it, and you have to modify the table. So this table you have to modify it. So here functional dependency, see, whatever he given is SSN to e name, first functional dependency. Okay, so this is my table was there, so this is SSN to e name, functional dependency is there. So in this column you have to check two rows are same or not. So in this, if you saw here, these two are same, no, so we can't do anything, we have to skip, we have to leave that functional dependency. Okay, so then next what we have to do is we have to check the next functional dependency, that is e number can derive p name and p location. Okay, so here p number, here p number is there. Okay, so p number to p name and p location. Okay, p number, p name and p location. Okay, so here, okay, so in this step what we are doing is we are checking these two are same or not. Okay, so if you saw these two are same, no. Okay, so that functional dependency also we can't use it. Okay, then third one we'll check it, SSN and p number both together should be same, then we have to check for hours. Okay, so first we'll check two rows contain same values or not for SSN and p number. Okay, so here for SSN, so first of all SSNs are different, so no point of seeing p number also. Okay, so these are also different only. So all three functional dependencies we saw, so none of the values in the row are the same for x to y functional dependency. So we can't modify any of the cells in this matrix. So this cell remains same. Okay, so that matrix will not change anything. Okay, so this, since it's not changing anything, then we'll see the result. For result, here this row contain all A's, no, this row contain all A's, no. Okay, that is, so I think here I missed, this is A1. Okay, so here it has to come as a A1. Okay, so I think by mistake it came here. Okay, so here this is B11 has to come, here A1 has to come. Okay, so it's by mistake it came. So none of the rows contain, okay, all A's. So we can conclude as this is non-additive joint property. Okay, not there. Okay, so non-additive joint property not there. Okay, so this means this whatever decomposition we did, this is lossy decomposition. So somewhere data will miss it, or we can produce unwanted spurious tuples. Okay, so this what will happen. Okay, so next property we'll see it in next class.